Keep your video on though. Video. Good afternoon, everybody. I'm Melissa Rebeck. I'm from the board of the Australian New Zealand Biochar Industry Group, and my company Carbon Drawdown Projects is sponsoring this webinar. And thank you for coming in. We'll get started as more people enter into this webinar. And it's about biochar and nitrous oxide reduction. And I'd really like to make a warm welcome to our panel, Professor Stephen Joseph, who's going to wave, Professor Annette Cowie, and Professor Lucas van Zwieten. This webinar came about from discussions with Fertilizer Australia, and hence Australia New Zealand Biochar Industry Group have put this webinar on. Today we're going to cover off on how biochar reduces nitrous oxide emissions from fertilizers. That's going to be presented by Lucas. Also, Professor Stephen Joseph is going to cover off on how fertilizer and biochar are already being used on a big scale in China and the US and other elements. And Professor Annette Cowie is going to cover off on how can the fertilizer industry capitalise on the carbon market by using biochar. Before we go into those, just some background. The Australia New Zealand Biochar Industry Group has been an organisation running since about 2016 and became an industry group in late 2018, early 2019. The membership has grown in that time, and we're now over 200 members, and 20 plus of those are doing multi-million-dollar projects. And just last year, we launched, or early this year, we launched our roadmap, and we have 10 priority initiatives and a range of themes, and we're in the process of having leaders of each of those initiatives, and we plan to scale up the industry to a minimum $5 billion industry by 2030. There's a QR code there in the bottom, which you can access the roadmap, but also a range of our resources and network and contacts. I just wanted to cover off on what is biochar for those that are not familiar. Biochar is no longer a cottage industry. There's large-scale pyrolysis and units and gasifiers that are now making biochar. The concept of biochar is more than the black substance, which is very special in itself. Biochar is made from any once living bio waste, and that can be anything from trees to biosolids. In the process of making biochar in a pyrolysis reactor or a gasifier, everything that is burnt off is captured as an energy in the form of heat energy. It can be biodiesel, renewable diesel, and even hydrogen. Everything else that remains is biochar, and that can be 50 to 80% carbon, and that depends on the unit itself and the temperature at which it's produced and the feedstock. The messages that we're hearing from the fertilizer industry are that there's concern about the consistency of the feedstock. ANSBIG's established a code of practice which classifies 3 grades of biochars to fit for purpose. Fit for purpose biochars can now be made that are specific to the needs of the fertilizer industry. Considering how that is made, there needs to be consideration for the type of feedstock used, the temperature in which it's processed, and the type of technology. But because the industry is scaling up and there are large quantities of feedstocks being processed, the message that I'd like to get through is that a fit-for-purpose char could be made for your own needs and in large quantities. And one of the things I do through my own company is help establish those business cases and connections through to the technologies and the feedstocks. And the last slide I'm going to show in this part of my discussion is the range of technologies. Anything, the cottage industry has been the stoves and the Kentucky type kilns, but if you look down the bottom of this slide, down to continuous kilns, which now process anywhere from 500 kilos up to 5 tonne per hour. And those continuous kilns are those that produce the renewable energy and other heat energy and byproducts. So I'm just going to leave that there for now, and I just want to remind you to please put your questions into the chat as you go. We're going to save all of our questions until the end, but we will make sure we have 15 minutes at the end for questions. So without much further ado, I'd like to introduce our first speaker. If Professor Lucas van Zwieten can please share your video and your slides. Lucas is a Principal Research Scientist for Soil and Water R&D at the New South Wales Department of Primary Industries. And I'll hand it over to you now, Lucas. Thank you.
Thank you very much, Melissa, and also thanks for the brief introduction on biochar. It saved me a little bit of time there as well. I've got quite a few co-authors here, and thank in particular Stephen and Annette for co-authoring this work. So this is really a bit of a snapshot of a new book chapter in Biochar for Environmental Management. So the last edition of this book came out in 2015, and Professor Johannes Lehmann from Cornell last year started the process of the third and what he believes the final edition of this book. So what we see here is a snapshot of, I guess, the ultimate finding. So I'm actually starting off with my conclusion here, and from this we'll work into some of the finer details of why biochar might lower emissions of nitrous oxide and potentially methane as well. So we critically evaluated actually about 30 meta-analyses in the literature from 2015 up to 2023. And those 30-odd meta-analyses looked at probably 400 plus papers assessing changes to emissions of nitrous oxide and methane from incubation studies, from large-scale field studies, from long-term field studies in both dry land, in paddy systems, in forest systems. We ended up selecting 13 meta-analyses to really focus our assessment on, just due to the fact that these were high-quality meta-analyses. So the details of these meta-analyses will be in that book, which will be published early next year, I believe. So the key finding in dryland cropping, when biochar is used, we had up to 49% less emission of nitrous oxide. Now, the majority of these studies were where systems included fertilizer, with the majority of fertilizer being urea. There were mixed effects in dryland cropping on methane. It really didn't have a major effect, but we had, in some cases, less, in some cases, greater methane emissions. In paddy systems, there's a lot of studies, in particular coming out of China, around emissions in paddy systems. And what they showed there is up to 22% less nitrous oxide with biochar application, but importantly as well, a lot less methane emissions in those systems. So the conclusion here is that there are some significant opportunities to lower emissions of both nitrous oxide and methane from agricultural systems. We drill down a little bit. A lot of this data is again explained in a lot more detail in the book chapter, but here I'm loaning some meta-analysis that we did back in 2014 and 2015. And in this particular case, just having a look at feedstock. So on the x-axis, along the line on the bottom, we can see numbers, sort of 0, and then we had increase, which will be 100, or decrease, which will be minus 100% compared to a control. So in this case, we have a look at some different feedstocks that were added as biochar into soil. And importantly, what we see is the lignocellulosic wastes, the herbaceous materials, the wood biochars, all had around 50% mitigation of greenhouse gas emissions, nitrous oxide emissions from soil. But you look at the manure biochars, ones made from biosolids or manure or bio waste, they tended to have lower benefits to lowering emissions of nitrous oxide. And I'll go into some of those reasons in a moment. Other reasons why we get changes in nitrous oxide emission or other factors influencing the change are the dose. That's how much biochar is actually added into soil. So under 1% weight for weight, which works out at about 10 tonnes per hectare, so very, very high rate still. We had reductions of about 25%, but not statistically different. Between 10 and 20 tonnes, we started getting significant difference. And if we go all the way up to 10% biochar in the system, we had nearly 100% mitigation of nitrous oxide in those soils. Now, this is a really important finding, I think, in that many agricultural systems won't be able to afford to apply those rates of biochar to get this effect on nitrous oxide. But I think we've got some solutions here, and I'll raise them in a minute. And some of the other key factors associated with the biochar are around the hydrogen to carbon ratio, the molar HC ratio. And this really is a factor of both the feedstock. So materials or biochars with a HC ratio of below 0.3 tend to be ones that are very condensed. Most of the hydrogen's left the carbon matrix already, and you're left with a very, very strong aromatic structure. And when we start getting hydrogen carbon ratios above 0.5, our efficacy goes right down. So what influences this are both the feedstock and the processing conditions, in particular the temperature and the time of pyrolysis. So the more pyrolysed the material is, the better it is at lowering emissions of nitrous oxide. In our book chapter, this is another sneak peek from some of the key findings of the book chapter. We summarise the mechanism. So I've gone straight into the summary here of mechanisms, and we'll just focus here on the one on the left, which is around the nitrous oxide. Why do we get reductions in emissions of nitrous oxide when we're applying biochar in a fertilised system? So what we've found, what all the literature has found, is that the reactive nitrogen is sorbed to an extent onto the biochar in soil, and essentially we're lowering the availability of reactive nitrogen in the soil. So less substrate, less emission. A couple of the other factors, in particular, ones that we've done some research on, and I'll show some data later on, is around the NOS-Z gene. So that's when you have systems that are denitrifying. So when we're starting to denitrify nitrate through to ultimately N2 in acidic soils, the NOS-Z gene is often restricted at pHs of 5.5 or below. And what we found there is that some of the liming effect of biochar improves the denitrification. So where we do have denitrification, we get complete or more complete denitrification through to N2 rather than being stopped midway at N2O. We've also shown that biochar can shuttle electrons produced during organic matter breakdown, and that also itself stimulates complete denitrification through to N2. We've done some work just on purely the physico-chemical interactions of biochar and soil. So we know that biochar itself can actually directly sorb nitrous oxide and also react with nitrous oxide. And I'll show some data from a PhD student, Peter Quinn, on that work in a moment. And also we know that biochar alters a range of physico-chemical properties in soil, in particular gas diffusivity, and also poor connectivity in soil, and that alters gas movement and also water movement, and that itself can have some influence on nitrous oxide. I don't have time to go into the mechanisms of methane at the moment, but the book chapter will have it all. Here we can see some work that we've done at Wollongbar DPI. Stephen Joseph was involved in a lot of this work from probably the mid-2000s, 2005, 2006. And we've got a range of field testing in using stable isotope methodologies, auto chamber, static chamber techniques for assessing changes to greenhouse gas emissions. This is one piece of data. It's probably a little bit complex to go into too much detail here, but we were assessing emissions of nitrous oxide in static chamber trials with a range of different soils. So we looked at calcareous soils, vertisol, ferrosol, and arenosol or tenosol. And what was very obvious with the biochar is that where we had mitigation of nitrous oxide, and we were talking 30, 40, 50% less nitrous oxide being produced, we had improved gene copy of the NOS-Z gene. And that really was quite closely correlated to nitrous oxide production. So again, biochar stimulated complete denitrification in systems that were denitrifying. This is work from Peter Quinn that he did as a part of his PhD based at Wollongbar. And on the left-hand side, we're just looking at nitrous oxide in headspace. So this is a completely abiotic system. It was a fully sterilized system. And we had a tube which had a matrix in it. So it had a combination of soil and biochar. And we also had a control, which was pure sand and also pure biochar. And what Peter did is he injected nitrous oxide in one end and measured the release rate of nitrous oxide into that headspace. So essentially, the movement of nitrous oxide through that matrix of soil and biochar. And what we found is basically the more biochar that was in the system, the less nitrous oxide moved through the system. And we go right down to panel D at the bottom. The black circle was pure sand. So the majority of nitrous oxide moved through the pure sand within 100 hours or so of the incubation. But what was very interesting is that we had virtually no nitrous oxide detected in the headspace when that chamber was filled purely with biochar. And we did a lot of work, and Stephen was quite involved in a lot of the microscopy here and a lot of the chemical analysis. It was very clear that biochar both sorbed the nitrous oxide, but importantly, reacted with the carbon matrix, and we ended up forming pyridine, pyrrole functional groups on the surface of biochar when we had nitrous oxide present. We didn't get those groups when nitrous oxide wasn't present. So we know that we've got evidence that we're getting direct reaction between the carbon matrix from biochar, that aromatic functionalized surface, and nitrous oxide. The other piece of evidence that Peter had, where he used micro CT scanning, and again we've got we're looking at a range of different soils here, and basically what he showed is that with biochar present, in particular in the vertisol and the ferrosol, in soils with a high clay content, we ended up with much greater porosity, much greater airspace. But what's also important is we have much greater connectivity of those pores. Less of an effect in the sandy soil, but certainly in those medium and heavier textured soils, there was a major impact on connectivity. And what that means is I think we start getting improved gas flow in the system. And one of the reasons why we might get lower nitrous oxide production is we get possibly less denitrification because we've got more oxygen flowing in through those systems. So yeah, there's a range of sort of biotic and abiotic factors at play here. Another really important use for the pyrolysis technology. So up until now, I've spoken about the results purely with biochar added to soil and then having a look at how fertilizer interacts in a farming system. Another key use of the pyrolysis technology is around things like manure and biomass management. This is a study we did, I think in about 2010, 2011, where we had a look at alternative use of biomass. Basically, we applied poultry litter to soil, which is a very common farming practice, or we took that same poultry litter, we pyrolyzed it, and we added that same amount of material to soil. And we had about 20%, 30% of the emissions of nitrous oxide where we pyrolyzed the poultry litter. At the same time, we had very similar improvements in crop productivity. So the same nitrogen uptake, but lower emissions of nitrous oxide. So yeah, some really nice results there around alternative use of feedstock. Again, I can share with you all this paper. It's a fairly detailed study around alternative use, in this case of sugarcane trash, where either we left the sugarcane trash, which is a leaf residue after harvest, on the surface, which is common practice, or we take that and we pyrolyze it. So what we know is that when you leave raw biomass on the surface, it can stimulate microbes. Those microbes are activated. They break down soil organic carbon to get nitrogen to enable them to break down the high carbon biomass. Where you have biochar present, that doesn't occur. But what's really important in this whole system is where we had urea present as a fertilizer, matched urea. With biochar, we had 30% of that urea taken up by the sugarcane. Where we just use the green trash, we only had 20% of that urea fertilizer taken up by the sugarcane. So essentially, where we had biochar present, we're increasing the fertilizer end use efficiency of that system. And that is potentially now another reason why we're getting less nitrous oxide produced in these systems. I'm not going to steal too much of Stephen Joseph's thunder here, but I think one of the key uses of biochar is going to be as an enhanced efficiency nitrogen fertilizer. I mentioned earlier that we need generally high doses of biochar in soil. And that is because we've got large areas within soil and we have distribution. So really to have that key benefit on lowering emissions, you want to have the nitrogen in close, or the reactive nitrogen nearby the biochar. And I think the best way to do that is with these enhanced efficiency fertilizers. This particular product is an early version of a nitrogen enriched fertilizer. Here's another example from a soil CRC project where we had a phosphorus enriched biochar, and this work is in a calcareous soil. And some of the key constraints in these calcareous soils is the rapid tie-up of P with the free calcium to form calcium phosphates, which are not particularly plant available. So we designed a bespoke phosphorus enriched biochar in this case, and Nigel Wilhelm from Sardi has been trialling that in the field now for I think 3 seasons, and he's getting some great results on those quite constrained soils. This is an assessment of some of those very early products. These were the ones that Stephen Joseph designed probably back in 2010, 2011. I think the design of these engineered products has come a long way since then. But what we did show is where we have matched N content, we definitely had lower emissions of nitrous oxide with the biochar product, not as low as where we had a polymer coated, the Syngenta polymer coated urea gave us a lowest emissions sort of on that high emission date on the 7th of January 2016. But yeah, certainly there are opportunities to lower emissions of nitrous oxide when these products are used. So in summary, biochar can't be used blind and expect a result. And we've all been saying this for a long time. You just can't go out, throw biochar out willy-nilly and expect to see something. I think you really need to design the actual purpose for adding biochar. What's it going to be used for? You need to design the biochar to actually deliver the result that you're after. Because as Melissa pointed out, there is almost an infinite range of products, and that's one of the challenges with biochar, is just a vast array of feedstocks that can be used, and now also these engineered biochars can also really expand our opportunities. But what we do know biochar can do is I've shown that with meta-analysis we can definitely lower emissions of nitrous oxide from soil. We know biochars carry nutrients from the feedstock. We know it makes an excellent platform material for enhanced efficiency fertilizer. And I think some of the key components of biochar for that are the fact that it's highly porous. We can use its structure, and basically we're embedding now the fertilizer within that structure, and it takes time to move out of that structure. It's a bit like the same mode of action almost as a polymer coat. The other reason I think why we're getting lower emissions is that in most cases we're getting improved plant growth. So we're getting greater root exploration of resources, which means that there's less reactive nitrogen remaining in soil, which means that there should be less nitrous oxide emissions. We know that we're getting... Thanks, Melissa. I'm nearly done here. We've got changed soil physical and chemical conditions, in particular pH, and definitely redox has been shown to be changed. and also we're getting changes to in particular the NOS-Z enzymes. And I think in a systems context, there are a lot of opportunities for alternative uses of biomass. So in summary, and I won't go through this in too much detail, but the use of the biochar, I've got 4 key uses. I think these are probably the low-hanging fruit. One is amending soil to lower emissions. We've got a pretty good understanding of how that does that with the mechanisms, but I think some of the limitations are how long does this effect last? And in many of the meta-analysis are kind of suggesting maybe 2 to 3 years is that effect. It's not a permanent effect. It's not like carbon sequestration, where we know the carbon's going to last for hundreds of years. Its impact on nitrous oxide tends to be shorter term. I think pyrolysis of manures is an absolute no-brainer. We limit substrate carbon availability, we limit nitrogen availability, but we still get a lot of the benefits, and they tend to be longer-term benefits from those manures. And we've also got a range of biosecurity, odor, material handling benefit. I think the biochars themselves, as I mentioned, make an excellent platform material for fertilizers. Again, Stephen will cover that in a bit more detail. And also some work that was done by Eunice, a PhD student at UNE, has been showing that biochar can be used in composting systems to lower emissions of direct and indirect greenhouse gases, again, nitrous oxide and ammonia. Look, I'll pull it up there, Melissa. I think it's time to hand over to Stephen.
Fantastic. Thank you, Lucas. Please remember to keep your questions coming into the Q&A. Panelists, please, if you are free, have a go at answering some of those as we go. So I'd just like to hand it over to Professor Stephen Joseph, who is a visiting professor at 5 universities, and as we call him in the Australia-New Zealand Biochar Industry Group, the godfather of biochar. Over to you, Stephen. Thank you. Just unmute yourself, Stephen, in the bottom left-hand corner.
Okay, thanks, Melissa. Yeah, Lucas and I have been on a very interesting journey over the last nearly 20 years now. I'm going to talk about some of the work that I've been doing in China and in Australia, and I'm doing a little bit of work in the USA. So the big announcement is that basically biochar compound NPK fertilizers are commercialized in China. We don't know exactly what the production rates are, but I've been told somewhere between 200,000 and 500,000 tonnes of the products are produced every year, mainly from biochar that comes out of bioenergy plants. And you can see the product on the right. They make a range of products for both horticulture and broadacre, rice, maize, soy. Less so in the USA, but there are companies now that are producing biochar NPK fertilizers. And most of these fertilizers are as a granule. So we're going to... Oops, why is it not? Okay, so a group of us got together. Annette and I spent many hours at night time finalizing this paper. And what we try to do is synthesize 15,000 papers and come up with some understanding of how biochars work and when they don't. And the thing that came out of all of this is that you needed to concentrate biochars in the rhizosphere, and you had to intimately mix the biochar with your fertilizer. Either you do this during the production process or you mix it later on in a separate production process. And so we explained why this was the case. And what we know now is that the roots of the plant will actually interact with the biochar and the biochar compound fertilizers. So what's in a biochar compound fertilizer? Basically, what you do is you take a biochar, you mix it with minerals, you mix it then with sources of N, P, and K, and you either granulate it or you pelletize it. Lucas showed you some pellets in the last. The big research effort was what sort of minerals do you pre-treat the biomass with minerals and then add the nutrients, or do you post-treat the biochar with minerals, or do you do both? And I don't have enough time to talk through all of these things, but basically what we're finding is that the minerals are really important for reducing greenhouse gas emissions and also for enhancing nitrogen uptake efficiency. So what we find is that if you add biochar that's loaded with macro and micronutrients, and you put that biochar near the seed or the seedling, and those roots then interact with the biochar, the plant spends less energy in actually taking up the nutrients. Okay, so this was a picture of one of the first products we developed in China. It's basically wheat straw biochar with 5 to 7% clay, and that the biochar was produced at 450 degrees C in a rotary kiln. And then there was some more clay added and mixed with urea and DAP and superphosphate, and then it was granulated in a steam environment. You can see the X-ray analysis down the bottom here, the high N content, the high P, and the high K content. We published this paper 2014. Basically, what the hypothesis was is that we could replace about 20 to 25% of NPK with a biochar, make a granule, and we could increase yield and reduce nitrous oxide emissions. So these are some, we also hypothesized that we could reduce methane emissions as well. So this is the results. You can see here that the wheat straw biochar compound fertilizer gave the lowest emissions and the greatest yield increase. Basically, when you started to look at more complex feedstocks like municipal solid waste, the results weren't as really, there was no difference between a standard granulated NPK fertilizer. We got good results with the peanut hull and the maize straw biochar. One of the things to understand is, as Lucas said, feedstocks are really important. The best feedstocks for getting a high reduction in greenhouse gas emissions and increased yields are straws. So wheat straw, maize straw, then hulls and nutshells, and especially bamboo. These, we don't exactly know why that's the case. It's very complicated. I'm not going to have time to talk about it, but if people are interested, I can give them some papers that go into this reason. Okay, so one of the first things we did, my background's in material science and chemical engineering. I did my honours thesis in electron microscopy. So I was really interested to see what happens when we mix clay and wheat straw biochar and diammonium phosphate and urea and superphosphate. And what we basically found is that the biochar had reacted with the chemicals. And in particular, the chemicals had, during the granulation process, had migrated into the pores of biochar. And we actually, doing some very high-end analysis, was able to show that especially the urea reacted with the wheat straw biochar to produce what are known as cyclic anhydrides, so carboxylic urea derivatives. And we think one of the reasons why we got this increase in nitrogen use efficiency and decrease in nitrous oxide was because of these chemical reactions. I forgot to put the reference, but we published a very nice paper looking at mechanisms that take place at the roots, and also what happens when you use a biochar compound fertilizer versus using a straight mineral fertilizer. Because I'm limited in time, I just like to say, when you have a biochar where the pores are loaded with nutrients, and it's
2 minutes, Stephen.
Yeah, it sits on the roots, you actually change the root membrane potential, and the energy required by the plant to take up these nutrients is reduced. Right, coming towards the end, Melissa, one of the things that we are now focusing on is doing liquid biochar fertilizers. This is some field trials we're doing down in the south of New South Wales, where we're applying between 200 and 700 kilograms a hectare of biochar, mineral, high nutrient liquid fertilizers. The results are pretty amazing. After 4 months at applying 200 kilograms a hectare, we're seeing 37% increase in yield. I just wanted to show you this one where basically we made a special engineered biochar similar to some of the work I'm doing with Lucas for South Australia. 400 kilograms of biochar with 300 kilograms of minerals. And we added, instead of adding chemicals, we added an organic liquid fertilizer called Charlie Carp. And we applied both the biochar with Charlie Carp and the biochar with urea, no difference, but we got 100% increase in pasture yield. I must admit, we fell over backwards when we got those results. I just wanted to finish up the just emphasizing what Lucas said. When you apply these biochars in the rhizosphere, you not only change microbial dynamics, you change water dynamics, you change soil pH and EH, and more importantly, and we haven't talked about this, what we're seeing is changes in reactive oxygen species, and this is a whole nother topic that's fascinating. Biochar has this ability to either accept or donate electrons, but it also has the ability to either scavenge reactive oxygen species or to actually produce oxygen, reactive oxygen species. And it's an area that is starting to get a lot of research, because it's an unusual phenomenon that you don't normally associate with nitrogen uptake efficiency and nitrous oxide and methane production. I'd like to end with saying we're on a journey. We're starting to understand how we can pre-treat and post-treat biochar to significantly reduce both methane and nitrous oxide emissions. And I think we don't have a lot of funding to do this research work, but I think our theoretical understanding is pretty complete now. All we now have to do is get the money to actually make different sorts of biochar and do the field trials to actually prove that these new improved engineered biochars really do make a difference. Okay, sorry, Melissa, I'm probably a few minutes over.
No, well done. Thanks, Stephen. That's a great way to end that. And please put your questions in the Q&A for Stephen. He may have a look at some of those as we continue on with our next speaker, Professor Annette Cowie, who is the Senior Principal Researcher Scientist for Climate at New South Wales DPI. I'm not giving everybody's bios justice, but we don't have time. You can Google Annette, and I'll hand it over to you. Thank you, Annette.
No worries. Is this working fine? Is it working, Melissa?
Perhaps if you just share from the beginning, we can see your slides at the side, but it looks yeah, that's better.
Yeah, okay, that was funny. All right, all good now. Okay, I'm going to change topic and just give you a really quick overview of the carbon market and where biochar fits in the carbon market. So we're interested in the carbon market fundamentally because we have the UNFCCC, the Framework Convention on Climate Change, and under that the Paris Agreement, in which all countries have come together to address this global challenge of limiting global warming, hopefully to well below 2 degrees, preferably no more than 1.5 degrees. And the Paris Agreement recognises that in order to do that, we need to reach global net zero in the second half of the century. So net zero is the position when all our anthropogenic emissions, nitrous oxide, methane, and CO2, are balanced by removals, and that's essentially carbon sequestration. And biochar can contribute to both sides of that balance. So just thinking about the mitigation contributions of biochar, we've been talking specifically today about reducing nitrous oxide emissions from soil, as you just heard from Lucas and Stephen. But normally when we talk about biochar, we're thinking about the carbon storage from biochar, because when you take biomass and pyrolyze it, you create a product that is essentially stable. It's persistent carbon. If you use it as a soil amendment, it's likely to stay there for centuries to millennia. There's another contribution that biochar can make to increasing soil carbon, and that's because in the presence of biochar and particular minerals, you can trap and protect the organic matter that's existing and the new organic matter leaking out of plant roots. And so you can actually continue to increase the soil carbon level in a process that we call negative priming. Some other contributions that biochar makes is that when you make biochar, you release a combustible syngas, and if you use that for energy generation, you can displace fossil fuels. And also, as Lucas was mentioning, if you take something like poultry litter, that when you use it in its raw form is going to release a lot of nitrous oxide, but you pyrolyze it instead, then you avoid those emissions. So all those contributions add up to a big benefit from using biochar. Now, the IPCC, the Intergovernmental Panel on Climate Change, recently released its 6th assessment report, and it produced this sort of stylistic trajectory of how to get to net zero. And the important things are that if we're going to stay below 1.5 degrees, then we're going to have to reach peak emissions in 2025, halve our CO2 by 2030, and reduce methane emissions by 30% by 2030. And we're going to need to meet the position of net zero CO2 in the early 2050s, and then net zero greenhouse gas emissions will come later in the century. But in order to do that, we need to fundamentally reduce our CO2 and our non-CO2 emissions, and at the same time ramp up our removals. So biochar can contribute to all those components of this trajectory. Having committed to the Paris Agreement, countries are now making their national commitments to net zero. There are now over 150 countries that have commitments to net zero, and Australia is no exception. Actually, each of our states already had a net zero commitment before we had one at the federal level, but all states are committed to meeting net zero by 2050 or earlier. And companies have also come on board. There are a lot of programs and initiatives internationally to encourage companies to take net zero targets or carbon neutrality targets. And here in Australia, we have the program called Climate Active that awards carbon neutrality status to a range of different things, to products and services, also to organisations, even to events and individual buildings, and also precincts. There's also another initiative arriving, which is the requirement for publicly listed companies to disclose their climate-related financial risks. And this is coming to Australia as well. So down the right-hand side, we have the papers that have been released by Treasury, and at the bottom, the exposure draft of the legislation that will be requiring Australian publicly listed companies and institutions to disclose their climate-related financial risks. And down the left side are various international initiatives, including in Europe. So as a result of all those, there are a lot of companies and jurisdictions that are wanting to reach carbon neutrality or net zero. And in order to do that, they need to balance their emissions with removals and offsets. So what I mean is that they need to quantify their net greenhouse gas emissions from all greenhouse gases. They need to reduce those as the first step. Then they need to reduce their net emissions by sequestering carbon if they have the opportunity to plant trees or build soil carbon or use biochar. And then to the extent that there are still residual emissions, they need to offset those. So offsetting means usually that you buy carbon credits in order to balance your remaining residual emissions. And those carbon credits could come from emissions reductions or removal activities that are undertaken by another entity, and you purchase the credits. So this is where emissions trading comes in. There are some compliance markets. So these are situations where companies have a mandated obligation to reduce their emissions, such as the EU ETS and also the large emitters in Australia under the safeguard mechanism. But there's also the voluntary carbon market, where individuals and companies can buy carbon credits, such as when you want to offset your emissions for a flight. And the most prominent players there are Verra and Gold Standard in that market. And as I mentioned, the carbon credits can be one of two types. They can be emissions reduction credits, where another entity has taken action, say, covering a manure pond to reduce the methane emissions. That's an emissions reduction credit, or a removal credit, such as from planting trees. This is a figure from the International Standard on Carbon Neutrality, which is currently in its final voting stages, and we hope to be released by the end of the year. And it's an example of how a company can reach net or carbon neutrality by firstly taking action to reduce its own emissions, and at the same time offsetting these emissions with credits. And these could be initially emissions reduction credits, but eventually it's going to need to ramp up removal credits and then ramp up its own internal removals so it can meet the position of net zero. As I mentioned before, there are several different ways that biochar systems can contribute to mitigation. So let's just look at these from this perspective of emissions trading. The reducing nitrous oxide emissions from applying biochar to your system is an emissions reduction, fairly obviously. Storing carbon in the biochar by pyrolysing it is a removal, as is that process I described as negative priming, another removal process. But when you're avoiding emissions through displaced fossil fuels or avoiding emissions from biomass handling, that's reducing somebody else's emissions. So these wouldn't normally create carbon credits for you who are running the biochar system, but somebody else could potentially create carbon credits if they have avoided fossil fuel emissions by using syngas from a biochar system instead.
2 minutes.
Thanks, Melissa. The IPCC has identified a range of different methods for carbon dioxide removal, and it's identified biochar as being one which is more durable than the more conventional credits that you hear about mostly, which are associated with afforestation or avoided deforestation and soil carbon, but maybe not as durable as those involving geological storage, such as DACS, direct air carbon capture and storage, but that is very expensive and a very energy hungry process, unlike biochar. There are a couple of voluntary carbon market platforms that create credits for biochar projects. Puro was the first one. It's based in Finland, but I would say that these platforms all create credits just based on the carbon stored in the biochar. They don't yet recognise the nitrous oxide reduction, for example. Microsoft is one of the companies that's purchased those Puro credits created from a project in Australia. The biochar credits are actually seen as very desirable, partly because of the increased durability of that carbon, the lower risk of reversal, and also because they're recognised to have these co-benefits for sustainable development. Lucas talked about, and Joey have spoken about yield advantages, increased nitrogen use efficiency, and there's a range of different benefits for sustainable development that come from using biochar that I don't have time to go into. Australia's carbon credit scheme, the ACCU scheme, has a range of different land-based methodologies, but none of them are about biochar at the moment. But we do have a new phase coming up that they're in the middle of implementing the recommendations from the Chubb review, which will allow for proponent-led method development. So we are waiting for this so that we have the opportunity to submit a proposal for biochar to be included in the ACCU scheme. There's a range of different integrity criteria that methods need to meet. This is to demonstrate that the credits are real, that the carbon has really been sequestered or emissions reduced, and that this is additional, it wouldn't have happened anyway, and that it's able to be counted in our inventory. And there is in fact an IPCC method, it's optional, that Australia could use to count the carbon in our inventory. And we are able to demonstrate that biochar does indeed meet the offset's integrity standards. And so biochar is indeed a promising option for mitigation. It's recognised as such, and carbon credits associated with biochar would certainly support the expansion of the biochar-based fertiliser market. Thank you.
Fantastic. Thank you so much, Annette, and our three professor panelists. It's been very a great presentation, lots of information, and we can tell by the Q&A there that there's a lot. So we will go into those questions. Just briefly, I just wanted to also just flick up so just bear with me, just a closing slide as well for your information while we ask the panelists to start looking at the Q&As. Sorry, bear with me. So I'm just going to the last slide here. So there is a little QR code there again, and just wanted to let you all know that in 29th of November, there is a forum conference in New South Wales, and each of the states are having their own state-based forum. So if you're interested, you can look at the QR code and go to our events page and register for that. And Don has certainly put a whole lot of information into the chat about what ANZBIG are doing. And behind my head, you can see a little QR code as well. And that is if you want to register, you're interested in any purchasing of any biochar, and we will certainly, as an industry, endeavour to link you up with those biochar providers suitable to your needs. So while that's sitting there, I just want to start looking at the Q&A. So I can ask all the panelists to please reshare their videos and turn their microphones on. And we will go, and just bearing in mind, we've got about 11 questions, so probably a minute for each question. If we do go a little bit over, please feel free to leave if you need to, but we'll endeavour to answer these questions as we go. So I've just the first question there from Ringa at Jefferies. Stephen, I'm just going to refer that one to you. Now, the 3 grades of different biochars from the standards, are you able to talk to that one, or should we email Ringa about that?
It's not a minute answer, but essentially at the moment we're looking at a standard for animal feed, a standard for agriculture, and a standard for non-agricultural use. I think that's the quick answer.
Thank you. And Ringa, we can certainly send you some more information on those. So there's a question there. I'm interested in papers for the reasons for straw biochars having great influence on N2O reductions. Lucas's paper that is that meta-analysis might cover off on some of those. Is there any other papers, Lucas, that you could recommend to have a look at there?
I think the 2014 meta-analysis that Maria Kaela did would be a great start. Yeah, look, the evidence is overwhelming that the wood-based and the straw-based biochars, when added on their own into soil, into an agricultural system, they're the ones that are most effective in lowering emissions, probably due in part to some of the liming effect, high surface area porosity, sorptivity.
Thanks, Lucas. I just wanted to also recognise Don Coyne, who's sitting in the background as CEO of Ansbig. He's not well today, and he's put a whole lot in the chat. And certainly you can also go to Ansbig and ask him, follow up any questions, send him any questions as well. Okay, there's one from Kyron Crane there. Stephen, would love to talk to you about your trials in New South Wales if possible. I think that might be a separate thing. So by all means, please, we'll connect you both up going forward. Renga's put another question. Thanks, Stephen, for another great presentation. Are these papers on biochar fertilizer compounds and liquid biochar fertilizer trials published, and where could I find them?
Yes, they are published. Go to Google Scholar, and if you type in my name in Google Scholar, you'll have to go through the papers, but if you send me an email, I can send you a few of the key papers. I think the paper that we did, that Daniel Russ, R-A-S-S-E, is a good one to start with. And the other one, which I talked to, is a paper called Shifting Paradigms, and I'm the first author of that. But yeah, just send me an email and I can send some of the papers to you.
And Lucas has certainly got a range of trials as well going on as well. So we might connect Lucas into some of those questions. This one might be for you, Annette. Councils also need to report on sustainability, or do they need to? If so, by when?
Okay, so maybe you're thinking about the Sustainable Development Goals, and these are obligations that countries have entered into. Australia does indeed report on our contributions to the Sustainable Development Goals and our achievements in meeting those targets. There's a very large number, hundreds of targets under the SDGs, the 17 goals that Australia is attempting to meet. Sub-national jurisdictions are also contributing to that. And so a wide range of sustainability issues are covered by the Sustainable Development Goals, and biochar can certainly help.
Thank you, Annette. Before we go to the next question, I just wanted to let everybody know this video will be shared with you as well and will be on the Ansbig website. Ian has got a question there. Is there any involvement with Fertilizer Australia? There seems to be a huge opportunity to create a new, more sustainable industry, jobs, new businesses here. We are reaching out, and this is our first, I guess, moving forward in the right direction with Fertilizer Australia. I know we've got a question there from Jeff Clark, who is the executive officer there, and we will definitely continue to forge that relationship, and I will follow up with Jeff Clark following this webinar to see what further interest might come our way to connect. There's a question there. Can I get the slides by Annette Cowie? The webinar will be presented on the Vimeo channel, and also, so if you Google Ansbig, we've got a YouTube channel, and will also be put onto our website. So that's the best way to get the slides. Gary Leeson, hi Stephen, how did you make liquid biochar? Wet mill or ball milling plus dispersion in liquid?
That particular, well, there was a couple of different methods. The TK was done in an emulsifier. There's a real art with making liquid biochar fertilizers. It's taken us a long time to figure out how to do it. The other one was made by a company in Melbourne called CHT. They had a special dispersing agent. You can do it in 44-gallon drums. That's how we started off doing it. But if you want to do it commercially, I recommend emulsifiers as the best way.
Thanks, Stephen. Someone's asked for Stephen's email address. Stephen, are you happy if Don puts that in the chat for someone to? Yeah. So there's some other questions in the chat, which I'll go to as well. So I think that's the end of those questions. So I'll go to the Q&A. Sorry, go to the chat now. So I noticed there was a question from Jeff Clark, if I've skipped over that somewhere.
Melissa,
in the answered ones.
I've answered a range of questions, including Jeff's
Okay, so
one.
some of
Yeah.
those have been answered and they've disappeared off the system. I see. Okay. All
They're
right.
still in
So
the system, but unanswered.
they're answered. Okay. So do you want to read that out? Because I think that'd be relevant to everybody where that is. I just can't find it. So please read it out, Lucas.
Oh, okay.
Question and the
So
answer.
Jeff's question was that there's concern that biochar might immobilize with the nitrogen as a process for lowering nitrous oxide, and I think the answer to that is that could be a good thing as well, and for the reason being that in many cropping systems, as most of the professionals here would know, nitrogen's loaded up at the start of a crop. I think there'd be opportunities to lower the reactive nitrogen or the quantity of reactive nitrogen when it's not needed, and use it more as a slow release fertilizer then. So I think by binding it short term might mean that there's more available N later in the crop or when the crop demand is higher. But I think there's a lot more work needed, Jeff, around nitrogen release curves, both from the engineered products, so how quickly and how much nitrogen comes out of these engineered biochar EENFs, and also how quickly does that bound reactive nitrogen on biochar re-release into soil if it's a biochar amended soil.
I mean, the other thing, Lucas, is all the work that's being now done mainly in China on iron modified biochars to get that redox wheel going.
Yeah.
Nitrates into ammonia and then forming nitrate type compounds on the surface of biochar. I mean, we didn't have time to talk to you about all the different ways people are looking at putting nitrogen into biochars, but it's very exciting, actually. We're learning a lot.
Yes. And so Jeff, I'm glad those questions have been answered there. And I think going forward, as part of our roadmap scale up, these are the questions that we want to answer as an industry and as part of our roadmap. And so we would be very interested to follow up with you about questions that might come through from the fertilizer industry and endeavour to, find the answers that we do have and research the answers that we don't have. Because engaging with the fertilizer industry is a very much important part of the industry, and I think from my perspective and from our industry perspective, using biochar in agriculture is the highest order use for biochar, because once it's applied to the soil, it continues on benefiting the soil, and in a number of ways, which Annette touched on, and the biochar uses in agriculture could be another whole day workshop. Speaking of workshops, Stephen Joseph is going to run a workshop in conjunction with the New South Wales Forum, which is the day before on the 28th. And it's an exceptional workshop, always lots of questions and answers. And there'll be other people that are speaking throughout that, and that program is available on ANSPIC website. I think we've answered most of those questions in the Q&A, but please do reach out via Don Coyne, or if you've got any other further questions, you can also email me at Melissa, melissa.rebeck, rebeck@gmail.com, and I'll endeavour to answer, put your question in the right direction and get those questions answered. We're very excited on the level of interest that we have received today from those related to the fertilizer industry. And so thank you, everybody, all the participants, for our audience for coming along, but a very, very special thanks to ANSPIC for hosting the webinar, and to our esteemed panel, Professor Annette Cowie, Professor Lucas van Zwieten, and Professor Stephen Joseph. So thank you very much, everybody. We'll leave that there, and we will get your quick Q&As off of the Zoom as well, and endeavour to get back to any of you that we haven't answered those questions for. So we'll leave that there. We're closing off on just over an hour and 5 minutes. Enjoy the rest of your day. Thank you. Bye.
biomass in a controlled process with limited oxygen called pyrolysis. This product is called biochar when it is used as a soil amendment or for other uses that store the carbon in a durable form. Through the use of these technologies, we can capture, utilize, and store carbon for the long term. We can reduce waste. We can produce clean and renewable bioenergy. And we can remove CO2 from the atmosphere. More than 50 million tons of residual biomass, including agricultural residues, green waste, and other organic waste, is burned or landfilled every year in Australia. This is a waste of a valuable resource. It also causes pollution, including greenhouse gas emissions. But these wasted resources can be turned into a solid form of carbon, biochar. Globally, every year, biochar could sustainably remove billions of tons of excess CO2 already in our atmosphere, while also enhancing food production and regenerating degraded lands. Over 99% of CO2 captured by biomass re-enters our atmosphere as part of the natural carbon cycle. Pyrolyzing wasted plant biomass into biochar intercepts the cycle and converts carbon into a form that is typically stable for centuries to millennia. Biochar is a sustainable and climate-friendly way to transform organic resources into a valuable carbon product and renewable energy for a circular, regenerative, new carbon economy. There are also many proven and emerging markets for biochar that increase profitability and reduce or draw down carbon. Agriculture, horticulture, livestock, cropping, animal feed to improve animal health and reduce methane emissions, soil carbon sequestration, water management and filtration, mine and land rehabilitation, building and construction. With more uses of biochar emerging, the global market is growing rapidly and is forecast to reach almost 4 billion by 2025. Australia is on the cusp of developing a world-leading biochar industry thanks to our testing, technologies, research, and high-potential resources. ANZBIG's Code of Practice is guiding industry best practice for sustainable production, classification, and safe use of biochar. Australia's industry is ready to scale up and create important economic, social, and environmental opportunities, becoming a billion-dollar industry by 2030. What is the next step? We need commitment and leadership from corporates, capital, government, entrepreneurs, and academics. The Australian Biochar Industry 2030 Roadmap outlines a pathway forward for biochar industry scale-up. The roadmap has the potential to remove existing CO2 from the atmosphere, equivalent to 10 to 15% of Australia's annual emissions, provide 10,000 to 20,000 jobs in regional and rural areas, improve soil health and agricultural productivity, restore degraded lands to their true capacity. You can help put a foot on the brakes for climate change. Here's how. Share this video. Find out more at anzbig.org. Support the 10 key initiatives of the Biochar Industry 2030 Roadmap. Both financial and non-financial resources will help. Contact us to find out more. Show your support by taking the Biochar Pledge as an individual or an organisation, or join the Friends of Biochar community via our website. Join ANZBIG. We look forward to welcoming you.